in a slightly non-standard context. Partly because those contexts do arise naturally, and these calculations are often done, and also because in your textbook you will see names of certain probability distributions, and I hope that in this segment you'll see that those are things that you already know how to do. And so what we're going to do first is we're going to review the binomial and hypergeometric, what they have in common. And what they have in common is that you are sampling and you're looking at successes among your samples. So you have in your mind success-failure trials, and you know how many trials you're going to have. You know how many times you're going to toss that coin. You know how many cards you're going to deal. And what you're doing is counting how many successes you get. So the number of trials is fixed, and it's the number of successes that's random. What we're going to do now is we're going to turn this around. We're going to say, I am going to keep sampling until I get 5 successes. So what's fixed there? It's my 5. I preordained it. I am going to keep sampling until I hit that number that I want. And so now the number of successes is going to be fixed. And there is a random number of trials needed to get that many successes. And that's going to be our variable. So it's how long I have to wait until I get a specified number of successes, and those variables are called waiting times. And the simplest number of successes to wait for is just 1. So we'll start that way by looking at how long you have to wait until you get the first success. And I'll do it in the context of rolling dice. So the problem that we're going to approach is I'm going to roll dice, and this die is going to be rolled until I see the face with 6 spots. The question says, what is the chance that I need 8 rolls? And I want to be really clear here. When I say, what is the chance that I need 8 rolls, I'm saying, what is the chance that I need exactly 8 rolls for this to happen? Not more than 8, but 8. So what's success in this problem? Well, it's the face with 6 spots. And so we are waiting until that one shows up. All right, so if 8 rolls are needed, then what happened on that 8th roll? It's rather special, is it not? That's right. On the 8th roll, we saw the face with 6 spots. What about the first 7? We better not have seen that face in those 7. And so there is one pattern that allows us to get the success for the first time on trial number 8. That is 7 failures in a row followed by a success. That's the only way. Can you find the chance of that? Absolutely you can. Not a 6 and not a 6 and not a 6, etc., etc., and then a 6. Multiplication rule. And the chance is 7 factors of 5 6, and then that last one is a 1/6, and that's about 4.5%. You can generalize this. I just chose 8 off the top of my head, but I could have chosen any other number, and if I had chosen a number that I'm going to call k, then the chance that it takes k rolls to get the first 6 would be, well, you have to have k minus 1 failures in a row, and then your success. And what I want you to notice is that k, the number of rolls to get the first 6, has no upper limit. You can imagine rolling and rolling and rolling and rolling and never getting that thing. There is no stop to this. So this is the first time you are seeing a variable that has infinitely many possible values, and it's discrete. And that's partly the reason I'm not going to pursue this, because our mathematics prerequisite that we have assumed is not quite up to infinities yet. So what we're going to do rather is just pretend we believe that this adds up to 100% if you go on adding and adding and adding and adding. Let's take a look at what the picture looks like. So here is the probability histogram given by this distribution. It's called the geometric distribution. Some of you will recognize this is a term in a geometric sequence. Every term is the previous term times 5/6. And these probabilities have this lovely exponential decay. Not everything is bell-shaped. And the distribution is called the geometric distribution. And its possible values are 1, 2, 3, 4, etc. The name is nice, but the focus is on the calculation. You are waiting till you get the first success, and so before that, you must have had all failures. Now, I'd like to examine this slightly differently. This is the chance that exactly 8 rolls are needed to get my first 6. Supposing I ask a slightly different question. So I'm going to keep rolling the die until the face with 6 spots appears. The same situation, I'm still waiting for the 6. What is the chance that more than 8 rolls are needed? Can we find that? I think so. We can start writing patterns, can we not? More than 8 rolls. So the smallest number we're allowed is 9. So 9 rolls needed for the first 6. That means I have to have 8 failures followed by a success. Could be 10. 9 failures followed by a success could be 11 and 12 and so on. And where do I stop? Unfortunately, I'm not allowed to stop. This thing goes on and on and on and on, and so you have infinitely many terms. Now, you can certainly find the chance of this. This is 5/6 to the 8th times a 6. This is 5/6 to the 9 times a 6th, and so on. You can find all of these. So you could go ahead and do that, and if you know how to sum an infinite number of terms, then you can do the algebra and you'll get an answer. But by now you know me well enough that that is not what I'm going to ask you to do. Surely there has to be a better way. And you can get that better way by just looking at the patterns that you wrote down. What did you have to write down? Absolutely, absolutely no other way. You have to write down 8 failures in a row. And then after that, so these are the 8 right here, and there's 8 here, and there's 8 here, and after that all kinds of stuff starts to happen. What do you want to happen after this? I tell you what, you don't care. You can follow that by any sequence at all, and you will have needed more than 8 rolls to get your first success. And if you needed more than 8 rolls to get your first success, certainly the first 8 things you wrote down had to be Fs. So what you've learned is that this pattern of length 8 Fs in a row, is just the same as needing more than 8 rolls to get the first success. So if you want the chance of more than 8 rolls to get the first success, all you have to do is find the chance of this pattern. And this is a lovely, easy little pattern whose chance is 5/6 to the power 8, and you're done. So the moral of the story is when you find yourself adding lots and lots of terms, or maybe you have to, but it's a good idea also to see if there are other ways of working. So the discussion thus far has been about weighting the number of independent trials till the first success. Well, I could be greedy and I could want more successes, and I'm just about to be greedy. So we are going to wait until the rth success. This has become a standard notation for the number of successes we're waiting for. R is some number that we have fixed in our heads, and just to make sure that it is a number and not a letter, why don't we write it down? I'm going to roll the die until 10 6s appear. I'm not satisfied with 1, I want 10. So R is 10. Well, if I want to wait till 10 6s, I'm going to have to roll for a while, and the question I'm asking is, what is the chance that I need 70 rolls? Do we know how to answer this? Well, let's recap what we did in the previous case. We said, well, that last roll, it has to be a 6. I think the same thing is true here. If 70 rolls are needed to get that 10th 6, then roll number 70 must be a 6. What about rolls number 1 through 69? Well, they don't all have to be 6s, certainly. They are not going to be all 6s. That's highly unlikely, and then our event won't occur. Roll number 70 is not just any old 6. It is the 10th 6. So in rolls 1 through 69, how many 6s must you have had? That's right. You must have had 9 6s, and that's the observation that is key to solving the problem. The 10th 6 appearing on roll 70 is the same as getting 9 6s in the first 69 rolls, and then a 6 on roll 70. So how do you do this? The chance of something and something else, the two events both have to occur, so multiplication rule. And that says take the chance of the first one and multiply by the conditional chance of the second given the first. Where did the conditioning go? Well, it went away because roll number 70 is independent of rolls 1 through 69. So I don't actually have to write that condition down. So the chance that I want is the chance of getting 9 6s anywhere in the first 69 rolls times the chance of getting a 6 on roll 70. Do we know how to do that? Yeah, we know how to do that. Let's take a look at, well, let's take a look at the second bit. The chance of getting a 6 on roll 70, surely that's the 1/6. What about the chance of getting 9 6s in 69 rolls? You have a method for doing that. That's called the binomial formula. And that's this piece here. So let's see what just happened there. This first term, that is the black term here, is the chance of getting 9 6s in 69 rolls. So it is found by the binomial formula. The number of trials is 69. Success is defined as getting a 6, so its chance is 1/6. And the number of successes that you want is 9. And you can get this value from either your probability calculator in your textbook or any other way. I got 0.0998. You might get something slightly different from your textbook's calculator because you have to round the 1/6, but it won't be far different. So you have a binomial term times the 1/6, and that's the chance of getting a 6 on roll 70. It doesn't matter what's happened before. And so if you work out the product, you have about 1.5%, just over that. These probabilities are called negative binomial probabilities. It's not the binomial turning negative. The negative binomial expansion is a piece of mathematics, and terms like this appear in it. And that is why negative binomial. I'm not going to be so focused on names. I would like you to notice that you can find probabilities to do with waiting times until however many successes by just thinking about, okay, what had to happen on that last trial? Now, where did we use independence? Well, we used independence in saying here you don't need the conditioning because the 70th roll doesn't depend on what happened in the first 69, and you also used independence inside this binomial distribution here. The logic did not rely on independence at all, and so what we're going to do now is shift the assumption slightly to sampling without replacement. Same thing, waiting for a success, but in sampling without replacement. And I will start, as we did before, by waiting till the first success in a particular context of cards. So I'm going to deal cards from a well-shuffled standard deck till a diamond has appeared. Let me remind you, the deck has 52 cards and there are 13 diamonds. And the question I'm asking is the chance that 6 cards have to be dealt for this to happen. And what does that mean? As we said before, this means that on the 6th card, you had your first diamond appear. Do we know how to do this? Absolutely, we've just done it a few minutes ago. The pattern is 5 non-diamonds in a row followed by a diamond. That's the only way this could happen. Can we find the chance of this? Sure we can. Not a diamond, and not a diamond, and not a diamond, and not a diamond. So what is the chance of that? Well, multiplication rule, and the chance is there are 13 diamonds, so the chance that the first one is not a diamond is 39 over 52. And now 38 over 51, and so on. Multiplication rule says just multiply the conditional probabilities. And so you have 5 non-diamonds in a row, and what must happen next? Well, you have 47 cards left, and you better get a diamond. How many diamonds are left in there? We haven't used any of them. So all 13 diamonds are left. And therefore, your chance is given by that product of fractions there. And it's about 6%. Very similar to not a 6 and not a 6 and not a 6 and not a 6 and then a 6. But there, of course, the 5/6 was the same every time. And here you change your factors because you are dealing without replacement. So that is one major difference between the two calculations. The other I'd like to point out is that in the case of waiting till you got a 6 in rolling a die, in theory you could be rolling a long time. Rolling and rolling and rolling. There is no upper limit to how many times you have to roll, but in the case of cards, there is most definitely an upper limit. You're going to run out of cards after a while. Your deck has only 52 cards in it. So it's worth noting that this variable, the number of cards that I have to deal till I get my first diamond, is limited. What's the smallest it can be? Yeah, 1. You get a diamond right away. What's the biggest it can be? Well, if you're waiting for a diamond, what's the worst case scenario for you? The worst case scenario for you is all of the non-diamonds show up first. So that's 39 of them in a row, and you're getting really tired. But once you've seen 39 non-diamonds in a row, card number 40 has to be your first diamond. And so the number of cards that you have to deal is going to be somewhere between 1 and 40. We wrote down the chance that it has to be 6. To finish the discussion, I'm going to be greedy again. And I'm not going to be satisfied with 1 heart. I am going to wait until I get 4 diamonds. Sorry, I wasn't even waiting for hearts before. I was waiting for diamonds. So, not waiting until 1 diamond. I'm waiting until 4 diamonds. Well, then I'm going to wait a little bit longer. And the question I'm asking is, what is the chance that 20 cards have to be dealt for this to happen? And now you know how to do this. What has to happen on that 20th card? It better be a diamond. Any old diamond? No, your 4th diamond. Therefore, what has to happen in the first 19 cards? Yes, you better get 3 diamonds in the 19 cards. And so the chance that you're trying to find is the chance of 3 diamonds in the first 19 cards and then a diamond on the next card. Can we find this? Yep. These 2 events both have to occur, so multiplication rule. The chance of 3 diamonds in the first 19 cards times, and now I cannot avoid that condition, the conditional chance of getting a diamond on card number 20, given that you have 3 diamonds in the first 19 cards. Because I'm sampling without replacement, I do have to keep those first 19 cards in mind, since I have said that there's going to be 3 diamonds in there. Right, so how do we do this? Well, do we know how to find the chance of 3 diamonds in 19 cards dealt from a deck? I think we do. That is what the hypergeometric was all about. You're dealing a bunch of cards from a deck. What is the chance of getting so many successes? So the answer looks like this. You have one hypergeometric term followed by a fraction, and let's see what those terms are. So this first term is the chance of getting 3 diamonds in 19 cards dealt from a randomly shuffled deck. So how does the hypergeometric work? Well, you need a population size. That's the deck size, 52. What are the good elements? You're waiting for diamonds. So the number of good elements in your deck is 13. How many are you sampling? You're sampling 19. That's what we decided. In the first 19 trials, we had to get a certain number of successes. So you're sampling 19, and you're looking for 3 successes. And so you'll recall, population size, choose sample size. In the denominator is the number of possible samples, and in the numerator you have good cards in the population, choose good cards in the sample, bad cards in the population, choose bad cards in the sample. This is your hypergeometric term, which you can find out how much it is by using your handy probability calculator in your textbook, or you can do the cancellation. So what's this? This is the conditional chance of getting a diamond on the next card, given that you have 3 diamonds in the first 19 cards. So how do we work that one out? You've dealt 19 cards. So how many cards do you have left? You have left 33 cards. And do you know anything about them? Yes, you do. You know that 3 of them were diamonds. So you have 33 cards left in your deck, of which 10 are diamonds because you used up 3 out of the original 13. And so the chance that you now get a diamond is 10 divided by 33. And that's your 0.3030. And if you multiply these two out, you get about 4 and a bit %. So you'll notice that this is the same logic as the problem we did before. How long do I have to wait until I got the so manyth 6 in rolls of a die? On the last one, you have to get that particular success, and the other successes have to come before. So what we've done here is we have used the binomial and the hypergeometric, not directly as in what is the chance of these many successes in these many trials, but by recognizing that other problems can use those ideas.